Next, we'll discuss heating curves. In this picture, we have the heating curve of a liquid, and we see that as we heat a liquid, as heat is added, then the temperature increases linearly until we reach a certain point, and that point is the boiling point. So in this case, we're looking at water, and at atmospheric pressure, when water reaches 100 degrees C, it begins to boil. So we heat the water until it reaches 100, but then it begins to boil. At this point, the temperature cannot increase further until all of the liquid has boiled off. At that point, if we have the liquid in an enclosed container where we can increase the temperature, then the temperature can again begin to increase. Let's look at figure 12.28 and use it to estimate the boiling point of water at an external pressure of 200 torr. So here we have the water vapor curve, and at 200 torr, the boiling point of water is falling in this region, and the number that most closely represents that temperature is 66 degrees C. Melting and freezing are opposite processes. As a solid is heated, its temperature rises and the molecules begin to vibrate more vigorously. Once the temperature reaches the melting point, the molecules have sufficient energy to overcome these intermolecular interactions and the solid begins to melt. Here we see the heating curve of a solid. In this case, we have ice. So as we increase the temperature of the ice, the temperature increases linearly until we reach the melting point. At that point, the temperature cannot change until all of the ice has been melted. Then, when all of the ice has been converted to water, the temperature of the water can then again begin to increase. As we heat a liquid or a solid until it reaches the melting or boiling point, those regions are governed by an equation we saw last semester. Q, or heat, is equal to mc sub s delta T. So in this region and in this region, we have the same equations governing how much heat is necessary to heat ice or heat water. Q equals mc sub s delta T. Delta T is the change in temperature from the beginning to in this case, the melting point, or the change in temperature from where we begin to the boiling point for water. So the C sub s is the only difference. In the first region, we use the C sub s for ice, and in the second region, we use the C sub s for water. Melting is an endothermic process, so we have to add heat in order to melt a solid. Freezing is an exothermic process, and so freezing requires the removal of heat. The heat of fusion is the amount of heat required to melt 1 mole of the solid. For water, we have the heat of fusion for water, and the heat of fusion is opposite of the heat of crystallization. These are equal and opposite entities. Okay, so it's generally much less than the heat of vaporization, and the heat of sublimation, meaning going from a solid to a gas, is equal to the delta H for the fusion plus the delta H for vaporization. Here we see some examples. For liquid water, the melting point is 0, and the delta H of fusion is 6.02 kilojoules per mole. For isopropyl alcohol, we have a much lower melting point, and the delta H of fusion is also lower because the intermolecular interactions are weaker. For acetone, we have a lower melting point, and the delta H of fusion is also lower than water. And for diethyl ether, we have a lower melting point, and the delta H of fusion actually is higher than water, which is interesting because diethyl ether is actually does not have hydrogen bonding, but it does have a larger molecular weight. Here we compare the heats of fusion and vaporization for water, rubbing alcohol, acetone, and diethyl ether on a bar graph. You can see that for all of them, the delta H for vaporization is higher than the delta H of fusion. In other words, it takes more energy to boil a substance than it does to melt it. Here we have the heating curve for water. You can see here that we have all of the phases of water represented. In this region, where we're going from, let me use the highlighter. In this region, where we're going from ice to the melting point of water, we are governed by the Q equals mc sub s delta T for water. In this region, where we're melting ice, we're governed by the delta H of fusion times the number of moles. In this region, where we're heating liquid water again, we're governed by Q equals mc sub s for water times delta T. And in this region, we're boiling water and we're governed by the delta H of vaporization times the number of moles. In region 5, we're heating steam and we're governed by our Q equals mc sub s delta T equation, where the C sub s is for steam. In the next few examples, we'll look at each segment separately. Here is region 1, region 2, region 3, region 4, and region 5. In segment 1, we're heating 1 mole of ice from, say, negative 25 degrees C up to the melting point. We're governed by the Q equation, where Q is equal to m C sub s delta T, where C sub s is the C sub s for ice. The mass of 1 mole of ice is 18 grams, so if we're heating 1 mole, our Q would be equal to 18 times 2.09 times T sub F minus T sub I. That's our final temperature minus our initial temperature. The final temperature is 0 and the initial temperature is 25. So our Q comes to 0.941 kilojoules. You see here that we're going from negative 25 to 0. In the next region, we're going to be looking at the melting of the ice. Notice that the temperature doesn't change here. Because the temperature doesn't change, we can't use the same equation. So for segment 2, our Q is governed by N, which is the number of moles, times the delta H of fusion. So in segment 2, we're melting 1 mole of ice at the melting point, which is 0 degrees C. Our N is 1 mole of ice, and our delta H of fusion for melting of ice is 6.02 kilojoules per mole. So the Q is 1 mole times 6.02 kilojoules per mole, so we get 6.02 kilojoules. Next, we'll be looking at segment 3, where all of our ice has been converted to water, and we're heating the water from 0 degrees C to the boiling point. So this is segment 3. We're heating 1 mole of water at 0 degrees C up to the boiling point at 100. And we're governed by the equation Q equals m C sub s delta T, where C sub s is the C sub s for water. So our Q is equal to 18 grams, because we have 1 mole of ice, times 4.18 joules per gram degrees C, that's the C sub s for water, times T sub F is 100 and T sub I is 0. So 100 minus 0. So we have our Q at 7.52 kilojoules. Next, we'll look at segment 4. Segment 4 is the boiling of the water. Notice the temperature doesn't change here, so we can't use the Q equals mc sub s delta T equation because delta T is 0. Our temperature isn't changing. So again, we have a Q where we have a delta H governing this region. So boiling 1 mole of water at the boiling point, where Q is equal to N times the delta H of vaporization. N is 1 mole because we're boiling 1 mole of ice. Well, now it's water. We're boiling it from water to steam. Our delta H of fusion is 40.7 kilojoules per mole for water, so that's 1 mole times 40.7 kilojoules per mole. So our Q is 40.7 kilojoules. In segment 5, we're heating steam, okay? So along this region, and notice that our temperature is increasing. So for segment 5, we have heating 1 mole of steam at 100 degrees C up to 125. Again, we have the Q is equal to mc sub s delta T equation because notice that T is changing. So we have 18 grams of ice because it's 1 mole. 2.01 joules per gram degree C is our C sub S for steam. And then we have 125, which is our T sub F, minus 100, which is our T sub I. So our Q is 0.904 kilojoules. So we add all of those together to get the total Q for the entire process.